Today's lesson's on implicit differentiation. Implicit differentiation is used to find the derivative or the slope of a curve which is not a function. Something that's not a function that you guys are all familiar with is a circle. So we'll be able to find the derivative of the circle. It can also be used for functions that are in explicit form. Most of the explicit forms that you guys are familiar with are just y equals equations. So let's go ahead and just talk about the difference between implicit and explicit equations. Explicit equations will be those of functions. So this one right here is a function. It's a parabola. So this is actually explicit. This one right here is of a line. It is also, if I go ahead and solve for y, explicit. On this next equation, I can solve for y, but I'd have to square root both sides. And this is also not a function, so this is considered implicit, as well as this last one. It'd be very difficult to solve for y. It's not a function. It's implicit. Here's the steps that we're going to use for implicit differentiation. The first thing we're going to do is we're going to differentiate both sides of the equation with respect to x, which means we're going to be taking the derivative of y with respect to x. So we're going to end up with a dy over dx. Remember, y prime and dy over dx are the same. I'm going to say that more times today than I even know how many times I'm going to say it, because it's so important that you guys know that y prime and dy over dx are exactly the same. The second thing we're going to do is we're going to collect all our all our y primes on one side of the equation. Now, this is also dy over dx's. So we can say we're going to collect all our dy over dx's on one side of the equation. And we're going to put everything without the y prime or without dy over dx's on the other side. We're then going to factor the y prime out on the one side. Remember, that's the same thing as saying we're going to factor out the dy over dx on one side. And then we're going to solve for that y prime. So our answer could read y prime or it could read dy over dx. These two things are exactly the same. I'm going to show you that in the first problem. It's your choice whether you use a y prime or dy over dx. So we'll go ahead and do this, find this derivative. Normally, every derivative we've done so far has always been a y equals equation. Notice how this one does not have y equals. We are going to take the derivative of this, x cubed, by saying, okay, this is an x. So the derivative of x cubed is 3x squared. Plus, the derivative, oh wait, this isn't an x. So I've got to take the derivative of this, y, like normal, bring this out in front, rewrite the y, and lower it by 1. But since this isn't an x, I need to add on a y prime. Then we're going to say this equals 0, because the derivative of 64 is 0. Now let me show you the derivative of this if I would have used dy over dx's. So 3x squared plus 3y squared dy over dx equals 0. Notice the only thing different is I put a dy over dx here and I put a y prime here. Remember, dy over dx and y prime mean exactly the same thing. So that was step number 1, differentiate both sides with respect to x. The second thing we're going to do is collect all our y primes on one side of the equation. I only have one term with a y prime. It's right here. We're going to leave that on the left-hand side, and I'm going to move the 3x squared to the other side. That makes my equation read 3y squared y prime equals negative 3x squared. I really cannot factor out in step number 3 the y prime because there's really only one term. So I'm just going to solve for y prime. So we're going to divide by 3y squared, divide by 3y squared, and I end up getting y prime is equal to, my 3's cancel, I get a negative x squared over y squared. This will allow me to plug in for any point and find the derivative at that point. Remember, derivative means slope of the tangent line to the curve. I've only done one example with implicit differentiation. Now we're going to do some more. So let's now look at this next example. This one's much more complicated than the first one because before we've learned about product rule. And we've always said we use product rule when we multiply two x's together. Now we need to realize that we're going to use product rule when we multiply any two variables together. So I'm going to have to use product rule twice. Right here in this first part because I'm multiplying x squared times y, and in the second part I'm going to have to use product rule because I'm multiplying y squared times x. So let's go ahead and get started on this. Product rule says first times the derivative of the second. Now, the derivative of a y is dy over dx, or y prime, plus the second, which is y, times the derivative of the first, which is 2x. Now I'm going to continue on, and I'm going to have to do the second part of the product, or the second term, which is another product rule. So I'll use green and black for this, so you guys can start to see the differences of where's the first term, what's the second term. So on this part, I'll say first, like we always do, product rule, times the derivative of the second, which is a 1, plus the second, which is an x, times the derivative of the first, which is 2y. Since it's not an x, I need to put a y prime with it. And then the derivative of negative 2 is 0. Now, I know there's a lot of you kind of wondering what is going on here again, so I wanted to review this just a little bit. So I did a product rule on this first term because I had two variables multiplied together. So my first was x squared, and my second, the derivative of a y, because it's not an x, the derivative of y would be 1. But we need to go ahead and put a y prime with it because it was not an x. Then we're going to say plus the second, so we just write the second term, times the derivative of the first, which is 2x. Continuing on, we had a second product rule. So we say plus the first is y squared, times the derivative of the second, which is 1, plus the second, which is the x, times the derivative of the first, which is a y. So we're going to take the derivative of y squared, which would be 2y, but since it's not an x, we have to put a y prime on it. And then we put equals 0. So that was the first step. Take the derivative with respect to x. Now the second step is to collect all my y primes on one side. So what I'm going to do is I'm going to underline all my terms with y prime. And I'm going to move everything to the other side that doesn't have a y prime. So these first two, or this term, x squared y prime, and this one, I'm going to rearrange it just a little bit so it says 2x y prime, 2x y prime, equals, we're moving that term to the other side and this term to the other side. So this actually makes it say negative 2xy, and I'd have a minus y squared. Third step, factor out the y primes. So I have a y prime here and a y prime here. Let's factor that out. So I have y prime times x squared plus 2xy equals negative 2xy minus y squared. Last thing we're supposed to do is solve for y prime. So I'm going to divide by x squared plus 2xy on both sides. X squared plus 2xy. Final answer, y prime, or dy over dx, whatever you're using, is negative 2xy minus y squared all over x squared plus 2xy. And I'm finished. We're back for more implicit differentiation. I think it's very important that we embrace this idea that y prime and dy over dx are the same. So in this next problem, I'm actually going to solve the problem twice, one using y primes and one using dy over dx's to show that they're exactly the same thing. And then I'm probably just going to stick with the dy over dx's for future topics that I talk about, because most of the time we're going to deal with variables other than just x's and y's, and so it's very important that our notation is correct on those. On this problem, I have a cotangent y. We know the derivative of cotangent x to be negative cosecant squared. Now it's not an x, so we're going to say it's negative cosecant squared y And because it's not an x, we're going to go ahead and put a y prime with it. Equals, well, on the right-hand side, the derivative of x is 1. And then we have minus the derivative of y is 1. But it's not just 1 that I'm going to write because it is a y. I have to put a y prime. So this actually looks pretty simple as we take this derivative. It may have seemed confusing. So I'm going to run through that. Cotangent, the derivative of cotangent is negative cosecant squared. Write what was after it, which was a y. Since it's not just an x, we have to remember to write a y prime. Equals the derivative of x is 1, and the derivative of y is 1, but it's not an x, so we have to put a y prime with it. Collect our y prime terms on one side of the equation. So I'm going to collect these two together, and I'm going to put them on the left-hand side. So I'm going to leave this negative cosecant squared y prime, on the left-hand side. I'm going to add the y prime to the other side. So I have plus y prime equals 1. At this point, I need to factor out those y prime. So I've got y prime times negative cosecant squared y plus 1 equals 1. Solve for y prime. So I'm going to divide the negative cosecant squared y plus 1 off both sides. And I come up with my final answer. Y prime equals negative 1 over cosecant squared y plus 1. Now I said I was going to do this problem twice, and I am. I'm going to show you using dy over dx's, and from here on I will continue to use dy over dx's. So this problem, if I was going to solve it using dy over dx's, I will still say the derivative of cotangent is negative cosecant squared y, but instead of putting a y prime, I'd write dy over dx, which is the same thing as y prime, equals the derivative of x, which is 1, minus the derivative of y is 1, and so instead of just putting a y prime, I'm going to put a dy over dx. Remember, we do that because this isn't an x, so we need to denote it that we're taking it with respect to x. Collect all our dy over dx's on one side. So I'm going to move my dy over dx to the left-hand side. I have negative cosecant squared y dy over dx plus dy over dx equals 1. Factor out my dy over dx. Remember, that is a y prime. So I end up with dy over dx times negative cosecant squared y plus 1 equals 1. Divide by negative cosecant squared y plus 1 on both sides. Negative cosecant squared y plus 1. To come up with my final answer, dy over dx equals negative 1 over cosecant squared y plus 1. And I need to make a little quick correction on that. That negative should be on the bottom with the cosecant. The same thing over here. This negative is actually with the cosecant. If I want to be technical, I should really write 1 minus cosecant squared y. So as you can see, I come up with the same answers. I'm going to continue to use this dy over dx notation. Okay, let's look at some more things on implicit differentiation. This next problem, it starts out by saying that we're going to find the two explicit functions. And there's reasons for doing this, and I'll get into those shortly. Let's go ahead and find the explicit functions. Explicit functions are when you solve for the y. So let's go ahead and get this y by itself. I end up getting x squared plus 16. I'm going to divide by 16 on both sides. Y squared equals x squared plus 16 divided by 16. And then I'm going to square root both sides, so I end up with the function plus or minus, or the two functions, I should say. Together they aren't a function. They're actually a hyperbola. So plus or minus the square root of x squared plus 16 all over 4, because the square root of 16 is 4. If I sketch these two functions, this is really fast sketch. They would look something along these lines, where this one would be the y equals the square root of x squared plus 16 over 4. And this one would be y equals negative square root of x squared plus 16 all over 4. Taking those explicit functions onto this next screen, I'm going to go ahead and copy down what the explicit function was. It was plus or minus the square root of x squared plus 16 all over 4. What I'm going to show you is that if I was to solve this implicitly, I will end up with the same answer as if I'm going to take the derivative of the two explicit functions. I am going to start out by solving this implicitly. It is much easier to solve this with implicit differentiation than using the other differentiation. So solving this implicitly, I'm going to end up with 32y, and then I'm going to put dy over dx. Remember I said I was going to continue to use dy over dx? And that's because this wasn't an x. Minus 2x equals 0. Now I need to solve for dy over dx, so I'm going to add 2x to both sides. I get 32y dy over dx equals 2x. Divide by 32y on both sides. And my dy over dx is equal to, it would be x over 16y. So let's go ahead and take the derivative of the explicit functions and see if we end up with the same answer. This would end up, I would want to rewrite this as plus or minus 1/4 x squared plus 16 to the 1/2 power. This will allow me to go ahead and say that y prime equals, bring this out in front, plus or minus 1/8. Rewrite what's on the inside, x squared plus 16, lower it by 1, negative 1/2, times the derivative of what's on the inside, which is a 2x. So I took the derivative of the x squared plus 16. And now I'm going to go ahead and simplify this as being plus or minus, this would be 1/4. And I'll go ahead and extend this out because this is also on the bottom of the fraction. X squared plus 16. And I have an x on the top. So I'm going to actually erase one that's up here on top. Now you guys are looking at this and saying these aren't the same. But they truly are the same. I'll show you why. If I go back to this explicit form before I took the derivative, I notice that it says 1/4 the square root of x squared plus 16. I'm going to solve for the x squared plus 16 part. So I'm going to multiply by plus or minus 4 on both sides, and I get plus or minus 4y on the left-hand side. So I'm going to replace this x squared plus 16 with a plus or minus 4y. So down here on the bottom, I now have 4 times plus or minus 4y, and I have x, and I have plus or minus sign out front. This does give me the same answers. Okay, I still ended up with x over 16y for my dy over dx. So it's much easier to use implicit differentiation than trying to use that explicit form. I have one more example I need to go through for implicit differentiation. I've thought about leaving this one off of this section, but because it's really key, and as far as it's the only time that we've actually been plugging in numbers, I want to go ahead and do one more implicit differentiation, and it's asking me to actually find that derivative at the indicated point. So I'll go run through this really quickly. Take the derivative of x cubed, which is 3x squared, plus we have 3y squared, dy over dx. Remember, I'm using the dy over dx instead of the y primes, equals, please pay attention that you do have product rule here. The two pieces I'm going to use is, this is going to be my first term, the 6x, and the second term is going to be y. So I'm going to start out by saying first times the derivative of the second, the derivative of y would be dy over dx, plus the second, y, times the derivative of the first, which would be 6. And then I'd have plus 0, which I don't need to write. This is, the derivative of that is 0. Collect my dy over dx's on one side. So I'm going to move everything to the left-hand side. That's a dy over dx. So we'll have 3y squared dy over dx minus 6x dy over dx equals, I'm going to move my 3x squared to the other side. So I have a 6y minus 3xy, or 3x squared. Third step, factor out your dy over dx. I'm going to take that out of both of these terms. I'm left with 3y squared minus 6x equals 6y minus 3x squared. Divide by 3y squared minus 6x on both sides. And my final answer would be dy over dx equals 6y minus 3x squared over 3y squared minus 6x. Now, it did tell me to evaluate this at 2, 3. So I'm going to plug in the 2 for all my x's and the 3 for all my y's. So this is my x value, this is my y value. So I have 6 times 3 minus 3 times 2 squared all over 3 times 3 squared minus 6 times 2. dy over dx comes out to be the number then of 18 minus 2 squared is 4 times 3 is 12. I have 27 minus 12. And I end up getting 6 over 15, which I could then reduce to be 2 all over 5. So just as it with regular derivatives, we have a general derivative, and then we have a more specific answer once you plug in the numbers.